Fortunately, there's actually a much easier way to write the electron configurations of atoms, and that's because the periodic table is actually organized in terms of atomic orbitals, as I'd like to show in the next few slides. Now, before I continue, this is the periodic table that most people are familiar with, and this is actually called the short form of the periodic table. In order to see how the periodic table is actually organized, it's actually useful to look at what we call the long form periodic table, where the lanthanoids and actinoids are placed in between the transition metals, which are shown here in yellow. So here we see that the periodic table is actually arranged in terms of atomic orbitals. On the far left-hand side of the periodic table in groups 1 and 2, we have the s block elements. On the far right-hand side of the periodic table in groups 13 to 18, we have the p block elements. In the middle of the periodic table in groups 3 to 12, we have the d block elements. And in between the d block elements are the lanthanoids and the actinoids, which comprise the f block elements. So here we see the advantage of the long form of the periodic table, because the long form of the periodic table correctly shows the position of the f block elements. So you may notice that the rows in the periodic table are numbered consecutively from top to bottom, 1 to 7, and these rows, or periods, represent the maximum principal quantum number for the orbitals in that row. So for example, for the first period, or the first row, we have a maximum principal quantum number of n equals 1. So this is where we find the 1s atomic orbital. For the second period, where we have n equals 2, we have the 2s and the 2p atomic orbitals, and so on. Another important point in the periodic table is the labeling of the d and the f orbitals. So the d orbitals are labeled as n-1, and the f orbitals are always labeled as n-2. And what that means is, to take an example, for period 6, where n equals 6, the s orbitals and the p orbitals are labeled 6s and 6p because they are labeled directly from the principal quantum number, but the d orbitals are labeled n-1. So in this case, for period 6, n equals 6, so we have 6 minus 1 equals 5, and so the d orbitals are labeled 5d. The f orbitals are labeled n-2, so in this case, where n equals 6, we have 6 minus 2, which equals 4, and so the f orbitals are labeled 4f. And similarly, the orbitals will be labeled for period 7. One final point is the energies of the atomic orbitals. So we see that the periodic table is arranged where the lowest energy atomic orbital, which is the 1s atomic orbital, is placed at the top of the periodic table. Right? So as we go down the periodic table, the energies of the atomic orbitals increase. So whereas the 1s atomic orbital is the lowest energy atomic orbital, when we move down the periodic table, we find the 2s atomic orbital is the next lowest energy, followed by the 2p atomic orbitals, which is the next lowest energy. And the next lowest energy then, after the 2p, would be the 3s atomic orbitals. And after the 3s atomic orbitals, the next lowest energy orbitals would be the 3p atomic orbitals, and so on. So here we see where the atomic orbitals are located in the short form of the periodic table. In groups 1 and 2, we have the s block elements. In groups 13 to 18, we have the p block elements. In groups 3 to 12, we have the d block elements. And at the bottom, in the lanthanoids and actinoids, we have the f block elements. Of course, here it's important to keep in mind that the f block elements are actually sandwiched in between the bottom of the d block elements, starting at period 6. Once again, it's important to remember that the d and f orbitals are labeled n-1 and n-2 respectively. It's also important to note that since we only have one s orbital for each value of n, and since each orbital can hold up to 2 electrons, we have 2 columns for the s block elements. For the p block elements, because we have 3 p orbitals, px, py, pz, and each of the p orbitals can each hold a maximum of 2 electrons, we have 6 columns, which are labeled 13 to 18. In the d block, we have 5 d orbitals, and since each of those 5 d orbitals can hold 2 electrons each, we have 10 columns in the d block. And finally, we have 7 f orbitals, and since each of those can hold 2 electrons each, we have 14 columns in the f block.
Here I hope to show you how easy it is to write the electron configuration for any element just based on its position in the periodic table. In this example, we are asked to write the electron configuration for phosphorus. And as we can see here, phosphorus has atomic number 15. This tells us that there are 15 protons, and since the atom is neutral, there are also 15 electrons. So these are the 15 electrons that we have to distribute amongst the atomic orbitals. So to write the electron configuration for phosphorus, we start at the very top at atomic number 1, and we just read across. So this would be 1s1, 1s2. Next we have 2s1, 2s2. Next we have 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Then we have 3s1, 3s2. Then we have 3p1, 3p2, 3p3. And this is the correct electron configuration for phosphorus. You can see here that we said we had 15 electrons, and if we count them up, we have 2 plus 2 plus 6 plus 2 plus 3 gives us a total of 15 electrons. So that's one way we can check our work. Now, if you notice this electron configuration, the way it's written, this part of the electron configuration, 1s2, 2s2, 2p6, this is the same electron configuration as the electron configuration for neon. And so as a shorthand, we can also write the condensed electron configuration for phosphorus, which we would write simply as neon, which represents the previous noble gas, and then we would have 3s2 just like before, and 3p3 just like before. So this is how we would write the condensed electron configuration for phosphorus.
Atoms with a lot of electrons can have electron configurations that are quite long. For example, aluminum, which should have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p1, as shown here. However, we can shorten this electron configuration by recognizing the fact that this part of the configuration, 1s2, 2s2, 2p6, is simply the electron configuration for neon, which is the nearest noble gas. So we can therefore write a shortened or condensed electron configuration by writing neon, which represents this part of the configuration, and then just writing the electron configuration for the highest energy electrons, 3s2, 3p1. Okay. These highest energy electrons are significant because these are the electrons that tend to be involved in forming chemical bonds. We can also write this electron configuration using a diagram using partial orbital diagrams, which shows only the highest energy sublevels that are being filled. So for example, for aluminum, which should have the electron configuration neon 3s2, 3p1, we would write one box to represent the 3s atomic orbital, and then 3 boxes to represent the 3p atomic orbitals, 3px, 3py, 3pz, for example. And then we would fill those atomic orbitals by placing 2 electrons, which are located in 3s atomic orbital. So those 2 electrons would go in the box for the 3s atomic orbital, with 1 electron in the spin-up position, and then the second electron in the spin-down position. And then we would place another electron, 1 electron, in the 3p atomic orbital. And that would be placed spin-up in the first or the leftmost box for the 3p atomic orbitals.